Welcome! In this explainer, which was prepared by Dr. Nima Mahdian, we're going to dive deep into the world of polynomial models. These are the powerful tools we use to really understand and even predict the behavior of all kinds of complex systems you see every day.
So, how do we even begin to describe a real-world process using math? Well, it all starts right here. I want you to think of this equation as our master key. It's the single starting point, the common ancestor for an entire family of models we're about to meet.
Okay, here's our game plan. We're going to start with the big picture, that master equation. Then we'll break it down and meet the individual pieces. After that, we'll build up from the simplest models to the more complex ones. And then the big payoff, how to choose the right model for your situation. All right, let's jump in.
So, what is this master formula really doing? At its heart, it's all about balance. It's basically saying that what a system is doing right now, its output, is just a mix of what we've put into it in the past and, all the random, unpredictable stuff that happens.
You see, the whole point of system identification is to look at some data from a system and find a mathematical story that explains it. And the real magic of this general equation is how flexible it is. By taking some of its parts and just setting them to one, we can basically switch them off. And by doing that, we can create all these different specialized models for all kinds of specific situations.
All right, now it's time to decode the symbols on our map. If that master equation is the blueprint for our house, then these polynomial operators, well, they're the actual bricks, the beams, the windows. They're the fundamental building blocks we're going to use. Think of these letters, A, B, C, as describing the system's personality. A is all about the system's own memory, right? How its own past affects its present. B describes how outside forces push it around. And C and D, they give us a language to describe the unique character of all that random noise. Seriously, getting these roles down is the key to everything that comes next. Okay, let's start our journey on the easiest path. We're going to look at models that are, frankly, just easy to solve, and that makes them a fantastic place to start.
Now, the key phrase here is linear function of known data. What does that actually mean for us? It means speed. It means we can solve for the best model parameters directly in one single calculation. There's no long, drawn-out process of guessing and checking. That makes these models incredibly fast and efficient.
First up, the FIR model. This is the simplest of them all. It basically says the output is nothing more than a weighted mix of a few recent inputs. That's it. It has zero memory of its own past actions. It just reacts. Think about tapping a bell. The sound you hear is just a series of fading echoes from that one single input.
Now, the ARX model. This is a major step up. We're switching on that A polynomial, the autoregressive part. Suddenly, the model has a memory of its own behavior, which lets it describe much more complex systems with feedback. But, and this is a big but, there's a catch. Notice how the noise, that E of t, gets filtered through the exact same A term? This model forces an assumption on us, that the system and the noise share the same dynamics. So, let's just boil it down. The big leap is in complexity. We go from the FIR model, which has no feedback at all, to the ARX model, which does. That gives ARX a lot more power, but it comes bundled with that really important assumption about the noise sharing the same characteristics as the system. And that question right there leads us to a super common problem in the real world. I mean, what if the random stuff messing with your system has a totally different vibe from the system itself? Well, for that, we're going to need a much more flexible set of tools. Let's see what they are.
All right, this next group of models is where we get the flexibility we've been looking for. These models let us describe the system's behavior and the noise's behavior as two separate things, which, let's be honest, is often way more realistic. But you knew there was a but coming, right? This flexibility comes at a price. We can't just do a single calculation anymore. Instead, we have to use an iterative process. It's like we make a guess, we check how wrong we are, we adjust our guess, and we repeat that loop over and over until we find the best answer. It's way more powerful for sure, but it also takes more computational muscle. The ARMAX model is a really nice middle ground. It adds that C polynomial, which gives the noise its own special characteristic. But it still shares that A polynomial with the system. Think about it like this. If turbulence hits an airplane wing, that disturbance has to travel through the whole plane structure, just like the pilot's controls do. They share some of the same path.
Now, the output error model, this one thinks about the world differently. It assumes you have this perfect, clean process happening, and all the randomness is just kind of sprinkled on top at the very end. This is the perfect model for when you think your noise is just measurement error, like a shaky camera trying to track a perfectly smooth robot arm. The arm's movement is precise, the camera just adds some jitter.
And finally, we get to the big one, the Box-Jenkins model. This is the most flexible, most powerful structure we have. Here, the system and the noise are living in completely separate worlds. Think of a chemical reactor. The chemistry inside follows its own set of rules. Meanwhile, the temperature in the room, which is a disturbance, is controlled by the building's thermostat. The two things are totally independent.
Phew! We've explored all the different paths and side roads on our map. So now, let's zoom out and see how this whole model zoo, as some people call it, actually fits together into a really elegant toolkit. And here it is, the big reveal. Just look at this diagram. You can see how by taking that big general model and just setting different parts to one, you get every other model. It shows you the whole family tree. The super complex Box-Jenkins can be simplified down to an ARMAX or an OE. They're all related. They all came from that one single equation we started with. It's beautiful, really.
Okay, this is a really critical point. The structure of the model you choose directly dictates how hard it is to find the answer. If you pick a simple structure, like FIR or ARX, you get a fast, direct solution. Easy. But if you need more flexibility and pick one of the more complex ones, you have to be prepared to use those slower, iterative methods. It's a direct trade-off.
So, after all that, how do you actually choose? Well, this table is your cheat sheet. It lays everything out. If you need something quick and dirty just to get a feel for your system, start with ARX. If you're pretty sure your problem is just sensor noise, go for an OE model. This is your practical guide for navigating that trade-off between model power and how long it's going to take your computer to run.
And this quote really gets to the heart of the whole thing. This isn't some philosophical quest to find the one true model of the universe. It's about being an engineer, being practical. The goal is always to find the simplest model that actually gets the job done for whatever you need to do, predicting, simulating, whatever it is.
And that brings us right back to where we started. We began with that one master equation, and we saw how, by truly understanding its basic building blocks, A, B, C, and the rest, we can build this entire toolkit of amazing models. You now have the concepts to navigate the trade-offs between simplicity and power to get real insight into pretty much any system. So the final question you should always ask isn't which model is true, but rather which model is useful.